We will continue our branch migration implementation plan by configuring our Internet access connection. We'll do that by first configuring routing and addressing services that are required for this connection, then verifying existing services that might be configured at the branch router. All of this is in preparation for the configuration of the IPsec VPN toward the headquarters router. Here's a high-level implementation plan. In this lesson, we will focus on configuring static routing and NAT as examples of required routing and addressing services, and also documenting and verifying other services that might be configured, such as DHCP. They could have an impact on the overall operations of the upcoming IPsec VPN connection and the overall operation of the branch router. The network topology shown in the top left panel will be used for this lesson and for all remaining lessons related to our implementation plan. Notice that we are connecting the branch router to the headquarters router already via a private WAN on the same subnet, 172.16.1.0. The private WAN is connecting the two private LANs, 10.1.1.0 for the branch and 10.2.2.0 for the headquarters. We have this new Internet connection. For the purposes of this demonstration, we'll assume that 192.168 networks are public addresses. For that reason, and because we are dealing with a public network, we're going to be doing network address translation. In fact, that's one of the things we'll configure in this lesson, and we'll use the address pool shown here. In this lesson, we'll start mentioning the security team that will be responsible for configuring the IPsec VPN on both routers, so we can focus on illustrating and understanding the impact of this connection in the routing and addressing services that we'll configure in this lesson. The first thing we will do is provide routing services toward the Internet connection. Our scenario indicates that this Internet connection is initially going to function as a backup of the private WAN in the process of migrating to an IPsec VPN-only scenario. Traffic goes through the private WAN, but when the private WAN goes down, we want to use the upcoming VPN to forward traffic toward headquarters. For this objective, we will use a simple alternative based on floating static routes. Other options include backup interfaces. The main connection via the private network is used for traffic paths because it is enabled for routing protocols, in our example EIGRP. We can verify that by using the show IP protocols command in our branch router. Here we find that we are running EIGRP, and this is advertising our LAN toward the headquarters using the 172.16 link. How has routing been accomplished? Let's take a look at the routing table. We can see here that the headquarters router is injecting a default route via EIGRP. Most likely, they are doing this by redistributing connected interfaces, or rather static interfaces, into EIGRP processes. You can see here the external EIGRP route with an administrative distance of 170. We are following default routing toward the headquarters and from there to the Internet initially. We should verify this at the headquarters router. So we go there and also verify the IP protocols running on it. You can tell that this router is running EIGRP, and it is advertising toward the private WAN. Everything else is reached via default routing. We go back to the branch and test connectivity to not only the LAN on the other side, 10.2.2.2, which is the LAN interface of the headquarters router, but also toward an example of an Internet public address, the public address of the headquarters router, 192.168.2.2. And we can also get there. By adding a floating static route and manipulating the administrative distance, we accomplish resiliency dynamically as soon as the branch router determines that routes disappear from the routing table upon failure. A floating route to the intended destinations will pop up in the routing table and direct traffic to the backup connection, which, in our example, will be the IPsec VPN interface. The floating static is simply a static route with an administrative distance greater than that of the existing routing protocol. In our example, we see that our routing table is showing the default route with an administrative distance of 170. So we should use something greater than that. We'll use 171 because of the administrative distance being shown by external EIGRP routes. You can see the administrative distance here in the routing table, or use show IP protocols to show the administrative distance used by the protocol itself. Let's configure that in our branch router. We'll use a static route, which will be a default toward the default gateway of the branch router, which is the ISP's IP address facing the branch router. You can tell that our branch router is 192.168.1.1. The default gateway for this router is 192.168.1.2. Here's where we set the administrative distance, and we're ready. We could do an initial verification here by using a rather dangerous command, debug IP routing, which could clutter your screen and become a problem in a production environment. But in the context of this demonstration, we are going to use it to illustrate how, when we go to the private WAN interface and shut it down, we can see, and we will undebug for the time being and focus on the display, we can see how the default route was deleted toward that private WAN. And immediately, a new route was found to the default destination and was added with an administrative distance of 171. So the backup route seems to be working. We cannot do further testing from the LAN interface or for LAN traffic because NAT is not yet configured. But we can display a routing table and verify that the static is ruling connectivity toward unknown destinations. We can also trace a public destination, such as the headquarters router's public interface, and verify that we are going across the 192 networks through the service provider. Before we configure NAT, we will follow the first recommendation of our security support team to implement some basic security and filtering in this internet-facing router. They will configure the firewalling and security controls in this router later. But for now, we will configure a basic access list and attach it to the internet-facing interface. It is called Internet Inbound, and it permits established traffic for return TCP connections and allows traffic into a certain server inside with a public address, which is the first number of our address pool for NAT. As you can see, it was excluded from the address pool. We permit pings and deny everything else, and then attach it to the public-facing interface. We'll show how this is impacted by the configuration of IPsec VPNs. Our next step is to configure NAT, and for that, we display the NAT configuration toolkit of commands that will be helpful during this demonstration. We're going to translate addresses coming from our LAN at the branch office and match those addresses with a NAT ACL that permits the subnet on the LAN. We'll then translate it into a global pool of addresses called NAT pool, which has that range of addresses according to our topology at the top. Everything comes together in our IPNAT inside source command, which matches the list of LAN addresses and translates them into the NAT pool, overloading the pool and thereby implementing PAT, port address translation. Look at the NAT pool command. It also starts with IPNAT. It defines the pool name and then the range of addresses. The net mask is very important here because it will define how the pool of addresses is navigated to generate global translated addresses. Part of our access list allowed or permitted traffic in to a certain host using a public address, 192.168.250.16. That's for inbound traffic, so we need to create a static translation for traffic coming inbound to match the static entry and always translate to the same internal host. For that, we need to create a static NAT translation pointing to 10.1.1.16, not shown in the diagram, but it is an internal server. That is an inside local address of the internal server. The inside global address of the server is 192.168.250.16. That matches our inbound ACL for destination addresses going into our branch. Among the verification steps shown at the top right, we can see the NAT translations by using Show IP NAT Translations and verifying there is nothing here because we have not generated any traffic. We see the static entry that was inserted as part of our inbound access policy. Another good verification step is Show IP NAT Statistics, which will display the pool we are using, start and end, and the ACL that matches traffic to be translated. Notice that we're also missing some configuration. There are no outside or inside interfaces configured for this particular NAT definition. In our example, the outside interface, the internet-facing interface, is set as IPNAT outside. The LAN interface is set as IPNAT inside. That's where the translation will take place. Let's verify the whole routing and configuration addressing by bringing down our private WAN interface again. We're going to bring it up first and wait for it to come up. Notice the EIGRP neighbor is reestablished and a new adjacency is formed. We're going to trace an internet public host. In our example, it will be the public address of the headquarters router. We will source it on our LAN interface. You can tell that while the private WAN is up, we are reaching the host via the private WAN. Let's debug IPNAT and see that if I bring the interface down, that should insert the backup route in the routing table after the EIGRP neighbor goes down. My trace should go through the internet connection while translating with the NAT definition. Let's try it. Repeat the trace and source it at the LAN-facing interface. Not only are we going through the public addresses and the ISP, but we're also translating our source packet into a public address from the NAT pool. This seems to be working, and we're reaching the internet across our internet connection. If you look at the top right panel, we illustrate what is going on. The private WAN is going down, and now we're using the internet connection. Our VPN is not configured, but we're preparing the router to be able to welcome this VPN connection and complete our scenario. In order for that to happen, we still must complete a couple of steps, shown at the top right. We need to verify existing services, which is one of the steps of the implementation plan. Why is this? We verified that using NAT, you need to prepare the router for the upcoming VPN connection. NAT pools initially, even without the VPN, must be advertised to the Internet. They must be reachable from the Internet. We have done this. Our service provider is pointing toward the branch router for return traffic into our NAT pools. DHCP is also important. It could be an initial source of information about which private addresses will be reachable across the VPN connection. Because of the structure of a VPN, the LAN will be considered part of the private network. The LAN on the headquarters will be considered part of the private network as well. The Internet connection is transparent. A special case of NAT verification is shown at the top. Overlapping IP subnets across a VPN could be a common scenario, especially when connecting different branch offices or different remote locations that may not belong to the same corporate network. In the example, we have 10.1.1 on both sides of the connection. If we have traffic that is considered private going from the 10.1.1 on the left to the 10.1.1 on the right, there will be overlap and there will be connectivity problems. The traffic on the left will think the destination is in its own local LAN and will not travel across the VPN. Let's undebug our branch router. If DHCP will be one of the main services to verify, let's refresh the commands to display information about DHCP pools, for instance, with a show IP DHCP pool command. We can see the pool of addresses being associated and assigned on our LAN-facing interface. We can see an indication of the utilization of the pool, and we can see the single address being leased. We can use other commands, show IP DHCP bindings, for instance, to display a particular binding. We can see the MAC address of the client using the IP address. The important thing to remember is that by looking at the pools of DHCP addresses, you can start preparing the VPN. Those will be the subnets you will most likely have to advertise toward the other side of the tunnel. Other verification steps include verifying our ACLs and security features. We have already added an ACL and assigned it to the Internet-facing interface, but there may be ACLs and other security controls blocking important protocols for VPN establishment. As you look at the top right panel, some of the protocols necessary for IPsec are listed. We've listed these before in our introductory lessons. We need to make sure the ACL is not blocking these. Protocol 50, Protocol 51, and port UDP 500 are the most important. In refreshing the access lists we have assigned to the router, we verify this ACL is not allowing IPsec traffic. We need to configure it and add those lines. In doing so, you will verify that the protocols and ports listed in the top right panel can be configured using keywords like ESP, AHP, and ISACAMP. Those are related to the protocols that belong to the IPsec definition. We put them at the top because we expect the bulk of our traffic to have matches against those lines. After migration, the main connectivity option will be the IPsec VPN. Other services you may need to verify are those that may alter or define the path of traffic, especially in the presence of dual connections. Our Internet connection is the backup of the private WAN. However, you could have things like policy routing. Why would you have policy routing in a branch scenario? Some of the trends we discussed concern WAN optimization. One of the tools to redirect traffic into a WAN optimization device, like the one shown in the figure, is policy-based routing, or PBR. Even in scenarios with stub networks like these, you may have PBR redirecting traffic into a WAN optimization device and then out to the WAN or the Internet. Another potential service that will have an impact on traffic paths is HSRP. Not in this example, but perhaps in regional office type scenarios, where you find redundancy at the edge router level. HSRP will define which router is active and servicing traffic flows. Therefore, that operation of HSRP, which will switch to another active router upon failure of the first, will define traffic flows. You need to be aware of this, as well as policy-based routing, to identify those traffic flows, determine how deterministic or non-deterministic they may be, and troubleshoot more accurately. Our lesson has been very productive in allowing us to configure basic services in our branch router and identify other services that have an impact in deployment. Our implementation plan calls for the verification and tuning of IPsec VPNs next. For that, we will call upon our security services team to start configuring the VPNs in our branch and headquarters routers. You can come back and verify and tune that deployment. Look at the impact of the service upon the services we have configured. Let's move on to our next lesson.